So hello, everyone. Welcome again. I hope you're all doing okay, finding ways to cope with the lack of social interaction. Today, we're going to continue talking about Gauss's law. This week, today we're going to continue talking about Gauss's law. We're going to introduce a new and then more generally about patterns of field in space. You can see from the virtual background behind me that this is a cube-shaped Gaussian surface. The electric field, which are the orange arrows, is pointing out from this surface. The cyan arrows are the n hats, which are of course different on every part of this cube-shaped surface. And then this is all due to a single positive charge inside the cube. So we're going to keep talking about Gauss's law. We're going to introduce a new law about magnetic field called Amperes Law. And then we're going to start a discussion of what are called Maxwell's equations, of which Gauss's law and Amperes law are a part. There are four equations that actually tell us what patterns of field in space are possible and what patterns of field in space are not possible. And once we get Maxwell's equations, we'll be able to use them to derive a very interesting kind of pattern of field in space. So that's the agenda. So I'm going to share my screen here. And let's see. There we go. And we'll start with a brief review of what we did last time. So on a surface, we can calculate something called the electric flux. So electric flux on a surface, it's used, the Greek letter capital phi is used to represent it because phi sounds like the beginning of flux. Or phi, I suppose, if we pronounced it correctly. And that's just defined as the dot product of the electric field on the surface and the outward pointing unit vector normal to the surface times the area of that piece of the surface. So it obviously has units of volts per meter times meters squared, so we end up with voltmeters. We did some examples in lecture and in recitation. We saw that if we have an area element delta A and we have an electric field on this piece of the area, we can draw n hat, and then we can calculate E dot n hat in the usual way. So it's either E sub x times the x component of n hat plus E sub y times the y component of n hat plus E sub z times the z component of n hat, or it's equal to the magnitude of E times the magnitude of n hat, which is 1, times the cosine of the angle between them, where this is the angle that we're interested in. And we use this to come up with Gauss's law, which you more or less could derive yourselves from what you now know about patterns of field, excuse me, and the charge distributions that make these patterns of field. And so Gauss's law, we found, is that the electric flux on a closed surface, so we have E dot n hat, and we write it in the most general form as an integral over a closed surface. But we saw that the surfaces on which we're going to evaluate this are ones in which we can usually do this integral by inspection. For example, we talked about the surface of a sphere where the field was always parallel to n hat. And this was equal to, or this was often, we approximate it by just summing up the electric field dot n hat delta A on finite pieces of a closed surface. And that was equal to the amount of charge inside the surface divided by epsilon 0. So this was Gauss's law. And we were able to use Gauss's law both to find the amount of charge inside a surface, or we can work backwards and calculate flux if we want to. Today we're going to use it for some other kinds of reasoning. We also looked at briefly at Gauss's law for magnetism, which said that the integral over a closed surface of the magnetic flux, which is just B dot n hat dA, was equal to 0, which meant that there were no magnetic charges or magnetic monopoles. We couldn't have a North Pole without a South Pole. We've just never found one. So let me find the chat window here. It's probably behind. There we go. Okay. Okay. So do you have any questions about that? So what we're going to do with this today is we are going to use Gauss's law to prove some things that we've only asserted in the past. There are two things it's often used for. One is to actually calculate an equation for a distance dependence, say, for electric fields based on the symmetry of a situation, but also to prove certain things about materials that are difficult or impossible to prove otherwise. So we're going to do the latter here. So one of the things is we asserted that in the past that there could be no excess charge on the surface of on the inside of a conductor. How do you spell excess? Now, this is plausible because excess charges are going to repel each other, and so of course charges are going to want to move toward the surface, so it made sense. But we weren't actually able to show, in the sense of a logical proof, a mathematical proof, that this had to be the case. But now we can, armed with Gauss's law. So let's consider now let's remember, first of all, something we did prove. So what we did prove, that the net electric field is 0 inside a conductor at equilibrium. And we did that by reminding ourselves that, that the drift speed of the average drift speed, this is an average, not a vector, of a mobile charge in a conductor was given by the mobility times the net electric field. And we also said that at equilibrium, our sort of definition of equilibrium was that the drift speed of mobile charges was zero. That means there is no real current flow or charge flow from one place to another. The charges could be moving around randomly in different directions, and that's fine, but the net average drift speed had to be zero, so no currents. And so it had to be the case, therefore, that inside a conductor at equilibrium, the net electric field had to be zero. And that's a real proof. This is a valid logical proof. Now, what we didn't prove, though, so we proved that the electric field, the net field, has to be zero inside a conductor, but we haven't yet proven that there's no excess charge inside a conductor. But we can now use Gauss's law to help us do that. So let's consider the following scenario. Here's some blobby piece of metal. And we'll put some charges outside it to polarize it. So here's a positive charge, here's a negative charge. And what that means is that the metal will polarize. So that E net is zero inside. But how do we know that there's none of these polarization charges ended up inside? Okay. So how can we prove that none of these charges are inside? So here's our polarized conductor. So what we're going to do, so this is in 3D. Of course, I'm taking drawing a cross-sectional picture here, but you can imagine a 3D blob. So what we're going to do here is we are going to construct a Gaussian surface that's inside the conductor, and it's a 3D surface. So again, it's some sort of blob-shaped 3D thing, and I'm simply drawing the outline here. So this is our Gaussian surface. And now what we're going to do is apply Gauss's law. So Gauss's law says that if we add up the electric flux all over this surface, that should give us the charge inside over epsilon zero. Well, what is the electric flux on this surface? Well, let's pick some location on the surface here. And we would take some little area element and multiply by E dot n hat. But we know that E is zero because the conductor is at equilibrium, and we proved this. And here E equals zero, and here E equals zero. So all over the surface, E is zero because the surface we've drawn, since it's a mathematical construct, we can draw it inside the metal. And so all over this surface, the electric field is zero. And therefore, the electric flux is 0. And this implies that the charge inside must be 0. So what do we mean by a Gaussian surface? Are there things that are not a Gaussian surface? So what we mean by a Gaussian surface is simply that we're constructing a closed, hollow, imaginary 3D surface. It's not made of anything real. It's a mathematical construct. It's completely closed, and it's hollow inside. So we're enclosing a piece of the metal here. And it's a surface to which we can apply Gauss's law. So there are things that are not a Gaussian surface. For example, we could have a surface that wasn't closed. We could just have like a soap film, a thin film, or a 2D object, and we can't apply Gauss's law to that because it's not a closed surface, so that we don't know what the inside, doesn't have an inside, basically. So we're talking about this mathematical construct. And it's completely legal to put our surface inside a material. I mean, that's fine because it's a mathematical construct. Now, you might argue that that we didn't draw the surface. So what about this space between the surface, the Gaussian surface, and the surface of the metal? Well, we can draw our surface, and we're constructing this 3D imaginary surface, so we can draw it arbitrarily close to the surface of the metal. So we can get closer and closer. We're going to get the same result as long as we're inside the metal. And so, in fact, this is a valid proof. Okay, so we okay with that? Okay, so let's try a slightly more complicated situation. Let's do the same thing. But now let's make this piece of metal hollow. So we'll put a hole in our metal so that this is solid, but here is a hole. And let's do what we did before. Let's polarize it. So what if there's a hole in the metal? You know, how do we know that there aren't some positive charges here and some negative charges there? Well, we start by drawing a different 3D Gaussian surface. Since we're interested now in charges inside the hole, we just want to make sure that our surface encloses this hole in the metal. So here's our Gaussian surface surrounding the hole. And since this surface is going through the metal, we know that the electric field is 0 everywhere on the surface. So we have, as we did before, we have the electric flux all over the surface is 0. So that implies that the charge inside equals 0, but it doesn't rule out this, that we have equal and opposite amounts of positive and negative charge here. And for that, we need to think about potential. So we're going to use the idea that that a round trip potential difference is zero, and this implies that delta V from A to B doesn't depend on the path you take. Since if we have two locations, A and B, we go this way, we get delta V1. If we take this path, we better also get delta V1, because if we take a round trip going here this way, and then if we go this way and then back around that way, that had better be a minus delta V1, and they better add up to 0. And so where we're going to choose our locations for our potential difference is we're going to put one location here, we'll call that A, and we'll put one location here and call that B. Actually, let's move B down here a little bit. And so the first path we'll take is just, we'll call it path 1. On path 1, actually, we're not going to get 0 here, right? Because clearly there would be an electric field pointing from the positive charges to the negative charges. And so this is, we're going with the field, so that's going to be less than 0. But now let's take path 2, where we don't go through the hole at all, we just go through the metal. So we'll call that path 2, and delta V, B minus, from A to B along path 2 must equal 0, since the electric field is 0. And now we have a contradiction. So basically what we're doing here is a proof by contradiction. We assume something. In this case, we assumed that there were charge inside the hole. And we followed this logic through, and we found that we got a contradiction, that we got a potential difference from A to B that was different depending on two paths. And that must mean that our initial assumption was wrong. So, whoops, I didn't mean to cross that out. I mean to cross this out. So in fact, we can't, there can be no charges inside the hole. So far we've proved two things. No excess charge inside a conductor at equilibrium, and to no excess charge inside a hole in conductor at equilibrium. What if we put a charged object in the hole? So let's see what happens here. So here's our metal, here's the hole. But now what we do is we put a positive charge there. Well, we can actually figure out exactly how much charge there's going to be due to the polarization of this object on different pieces of the surface. So the first thing we're going to do is, so presumably now this metal is going to polarize. So presumably what's going to happen is we would get some negative charge here on the inside of the hole and some positive charges on the outside. And we can see if that's true and actually how much we've got by judicious applications of Gauss's law. So the first thing we're going to do is draw a Gaussian surface that goes through the metal and surrounds the hole just like we did above. So here's our Gaussian surface. Since we're at equilibrium, it's still true that the electric field is zero everywhere on this surface. So that we know that the left-hand side of Gauss's law, the E dot n hat dA, the electric flux, has to be zero because E is zero inside the metal. And this implies that the charge, the total amount of charge inside has to be zero. And that says that tells us, but Q inside is the Q positive plus the negative charges due to polarization. That has to be zero. So that, for example, if this charge was a +3 nanocoulombs, we would have to conclude that on the inside of this surface, we would have a -3 nanocoulombs. So Q negative is minus Q positive. So we know exactly how much charge there is due to this polarization on the inside of this hole. Well, how much charge is there, positive charge is there on the outer surface? Well, to find that, we'll draw a different Gaussian surface that's actually here in the air. And so Gaussian surface 2. And for this surface, we know that, so here's Gauss's law, integral of E dot n hat dA, the electric flux, is equal to charge inside over epsilon 0. Well, we know that the total amount of charge here, the metal was neutral to start out with. So in fact, we're gonna, this needs to add up to, must be 3 nanocoulombs, and the charge inside is the positive charge plus the negative polarization charge plus the positive polarization charge on the surface. And these two things must equal 0. So in fact, we must have a plus 3 nanocoulombs here. And so the flux we get on this surface has to be due to the flux due to the 3 nanocoulomb charge that we put in to start with. So there's sort of some interesting things we can conclude from this. So given our current discussion, let's consider a question here. Thinking about Gauss's law, let's see if we can answer the following question. You're in your car and a thunderstorm is approaching. You can see that lightning is striking nearby, getting closer and closer. What should you do? What does Gauss's law tell you that you should do in this situation? Assuming your car isn't made of plastic. Well, almost all cars do have a metal frame, and that's a good point, but it turns out that your box doesn't actually have to be a completely solid box. So that so in fact, staying in the car is right, because what you want to do is stay in a place where the electric field is 0. And so inside this metal box, which is your car, or your car is at least partly a metal box, even if lightning hits your car, and so it gets charged very negatively on the outside, say, if we draw a Gaussian surface through the interior of this metal box, we find that because we're in a metal box, the electric flux is 0 because E is 0, which means that the charge inside is 0. So you're much safer staying in the car than you are getting out and having a chance of being exposed to large amounts of charge and current. So well done. We can also show, and I'm not going to do it right now because I don't want to take the time to do it at this point. We can also show something in the steady state. For example, in a current carrying wire. We can also use Gauss's law to show that that there's no charge inside this wire. And that's actually, I think it's worked out as an example in the book. But the basic idea is that we know that the electric field has to be uniform and parallel to the wire, and therefore the flux on any Gaussian surface we're going to draw here adds up to 0, and so there can't be any charge inside. So that's the basic idea. Okay, so I want to talk about Ampere's law, which is about magnetic fields. It's about patterns of magnetic field in space, which we know are really very different. And it's about taking a circular path and looking at magnetic field on a circular path, so more like potential differences. So here is some magnetic field. Here's a circular path. We measure magnetic field on this circular path, and we get that pattern. What pattern of conventional current could make that pattern of magnetic field? So the choices are a current out of the screen, through the circle, a current into the screen, through the circle, a current going around the circle clockwise, a current going around the circle counterclockwise, or zero current. Okay, so you think that it's a current coming out of the screen in the plus Z direction. So let's see, we have, if we point our fingers in the direction of I, and then we'd have an vector R to the observation location. I across R, I get going the other way if this current's coming out of the screen. So here's current out of the screen. Here's R, dl cross R. I would predict magnetic field going down. So let's try a current going into the screen. So we have current going into the screen to an observation location. Current in, that produces a magnetic field. Remember, we're talking about conventional current here, not electron current. So presumably, if there was a current carrying wire with a current going into the screen here, we get that pattern of magnetic field. So the basic idea is here that what we're going to do is consider a circular path and the magnetic field on that circular path. And we're going to consider the circular path, the surface, like a soap film stretched over a circular path, and the currents piercing that soap film. So if we drew this kind of edge on, it might look something like this, where we have a wire coming through our so here's our surface. There's a wire piercing the surface, and what we want to do is look at the magnetic field along that circular path and relate it to the value, the magnitude of the current that's, in this case, we have a current going that way. That's piercing this soap film. And so Ampere's law says that the integral of B dot dl around some closed path now is equal to some proportionality constant times the current enclosed. What does enclosed mean? It means pierces the soap film stretched across the path. And the proportionality constant is mu0. Now, there's an issue with signs here. Depending on whether we go clockwise or counterclockwise, we're going to get B dot dl being positive or negative. And so we are, by convention, going to take a path counterclockwise. From our viewpoint. So if we look down here along the direction of conventional current, and we take, in this drawing, we take our DLs going this way. If we take the path counterclockwise, then if the integral of B dot dl is greater than 0, so that means I is, oops, that was clockwise, sorry, counterclockwise. So we want to go counterclockwise. So if we get if in this case, if the integral, so in this case, if we take the integral of B dot dl, dl is opposite to B around this circle. So therefore we have a cosine of 180 degrees. And so this integral is going to be negative. So that means we're going to get a negative I, and that means that I is going into the circle. If we got a positive value, it would mean I is coming out of the circle. So the sign on this gives us the direction of the result. Now notice this is not flux, okay? This is the path integral or the line integral of B. We're adding up these B perpendicular DLs. This is exactly what we did with calculating potential differences, except that there's no negative sign here. Remember there we calculated E dot dl. So remember that B dot delta L is going to be the absolute value of B times the magnitude of delta L times cosine of theta, or bx delta x plus by delta y plus bz delta z. So it's something that's really very familiar with what we've been doing before. So let's look at so let's look at this path integral. We choose a counterclockwise path. Are we going to get a positive or a negative result? Okay, Charles, so hold on to your question about symmetry, because we'll see that we can actually use symmetry in a slightly different way in Ampere's law. It's a different kind of symmetry. Here we actually are using symmetry because we've carefully drawn our path in this situation, in a way that, notice that the magnitude of the magnetic field is constant along the path. And in fact, the direction of the magnetic field compared to the direction of dl is also constant along the path. So that's basically the symmetry here. So only two people are actually gonna guess about the sign of the sign of this integral here. Okay, yeah, you're right. It's positive because we have at every location here dl and b are indeed going in the same direction. Now, here's a slightly different question. So the question is, what is the value of this integral of b dot dl along this counterclockwise path? Now here's where our use of symmetry kicks in, because we basically need to evaluate b dot dl before we can do the integral. But in fact, that dot product is going to be the same no matter where we are along this path. Okay, so let's look at this integral. So we've got the integral of b dot dl, and that's the integral. Let's write it out. So at any location here, we find that b dot dl is going to be equal to the magnitude of b times the magnitude of dl times the cosine of 0 degrees, because they're in the same direction. So that's just going to equal the magnitude of b times the magnitude of dl. Well, note that the magnitude of b is a constant. We'll just say b. And the magnitude of dl is just dl. So this integral actually converts to b times dl, no longer vectors, with cosine 0 degrees. And since b is constant, we can actually take it outside the integral. So now what we have is b times the integral of dl around a circular path. Well, what is the integral of dl if we start here and we add up all the little dl's until we get back to the same location? That's just b times the circumference, which was a 2 pi r. So the answer is, in fact, 2. Now, one thing we can do with this is actually just get a value of the current. So if we know, we can do some numerical things. Suppose that the radius of this path is 3 centimeters. B is 1 times 10 to the minus 5 Tesla. What is I? Well, let's write down Amperes law again. The integral of b dot dl is mu 0 times I. What's the value of mu 0? Well, mu 0 over 4 pi is 1 times 10 to the minus 7. So mu 0 is just 4 pi times 10 to the minus 7. What is it? Tesla meter per ampere. So the way we'd figure this out is we'd go, so the left-hand side would be 2 pi r B is mu 0 I. So we have 2 pi times 0.03 meters times 1 times 10 to the minus 5th Tesla times, and we divide by 4 pi times 10 to the negative 7 Tesla meter per ampere. And that should give us I, which gives us 1.5. A different thing we could do with this is actually derive an expression for the magnetic field of a long straight wire. Remember that we did this using the Biot-Savart law. So we, in chapter 17, we used the magnetic field of a moving charge, which was mu 0 over 4 pi qv cross r hat over r squared. And then for a current, we got delta B is equal to mu 0 over 4 pi I delta L cross r hat over r squared for a little segment of a current. And we derive for a long wire, we got B of a long wire was mu 0 over 4 pi. Let me write that better. Mu 0 over 4 pi to I over R. Well, let's see what what Ampere's law would tell us. So we have the same picture here. So we have the integral of B dot dl is mu 0 I. We evaluated that for this picture here to be 2 pi r b equals mu 0 I. And so it must be that the magnetic, if we knew I, we would get the magnetic field is mu 0 I over 2 pi r, which if we multiply by 2 over 2, we get mu 0 times 2I over 4 pi times r. So we actually could derive the magnetic field of a long wire from Ampere's law without going through all the calculus. So that's an equivalent derivation. There are various other kinds of, there's some examples in the book of various other things we can derive in the textbook. We can get magnetic field of a solenoid this way, or so a solenoid, remember, is just a really long coil. It's got a big, strong magnetic field inside and almost nothing outside. And there's also a toroid. So questions about this in recitation, we'll practice applying Ampere's law to some concrete situations with numbers. I want to end this by talking briefly about Maxwell's equations. So Maxwell's equations are attributed to British physicist James Clerk Maxwell, and they are sort of a rather formal mathematical representation of the core of what we know about electric and magnetic fields, the possible patterns in space, and their relationship to the charge distribution that created them. So we already know two of them. So the first one is just Gauss's law. It's if we add up the electric flux over a closed surface, that tells us the charge inside divided by epsilon 0. So this is Gauss's law. And we saw that that was consistent with what we know of the electric field of a point charge, and therefore some superposition of electric fields of point distributions of point charges. And in fact, this is a somewhat more general and relativistically correct description of this. Now, there's also a way to write this in terms of differential calculus, but I think most of you haven't had that yet. If you want to see it, there is a section in the book that actually talks about that. And the second one is another thing we've already seen, B dot n hat dA, so the magnetic flux is equal to 0. So Gauss's law for magnetism, no magnetic monopoles, as far as we know. Yeah, really like grown-ups, Maxwell's equations. Then there's an equation that isn't quite complete. So we know that the round trip potential difference is 0, but there's some qualifiers. So what we need here is Faraday's law, which is a topic for next week. And we have Amperes law. So the integral of B dot dl is mu0 times the sum of the current inside, means piercing our surface. This is also incomplete. This is Amperes law. And Amperes law is not wrong. But we need a correction by, or an addition by Maxwell to make this complete. And we'll also see that next week. And these equations describe all possible configurations of fields in space. And if it's not consistent with these equations, then as far as we know, it's not possible. Can you derive electric field formulas with Gauss's law? Absolutely, you can. And in fact, one of the applications that we didn't get to in recitation on Tuesday is to describe, you can use Gauss's law to derive the electric field of a charged plate. In fact, it's kind of a lovely derivation. And you can also do a charged rod. So Gauss's law can be used in the same way to derive equations for electric field. This is in the textbook. So if you want to look at those, go for it. If we have time in recitation, we could look at one. Accelerating charges, stay tuned. That comes after Faraday's law. So accelerated charges are very cool. And we will see that 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 a lot of stuff all comes together when we start talking about accelerated charges, and we'll figure that part of that out by, in fact, applying Maxwell's equations. So stay tuned for a grand finale next week, Faraday's law.